Well, welcome back. I hope you're doing okay, and I'm sorry that I can't be there right now, but trust me when I say it's probably better that I'm here and you're there, lest you get this, which is no fun. Hopefully I'm back soon and everything's okay. But until I am, I want to make sure that we're at least making some progress, so we're not waiting on your progress for me just to not be sick. And hopefully we can do at least a little bit of that at distance. I know it's not perfect, but give it your best effort, and I know that this isn't exactly easy to learn on your own, or even with a good teacher when he's not sick, but we'll work together when I get back, and I promise the stuff clicks pretty well once you get it. And for the majority of you, it's just one step past where we started with 1D kinematics. So today I want to look at 2D kinematics just a little more carefully. So this is 2D kinematics. And what you might have noticed last night when you were reading was the equations had more subscripts. Like displacement now became like x or y instead of displacement. Now it's v initial x or v initial y. That's a typo there. Please ignore my ability to type right now. Or the acceleration now, it's not just a, it's ax or a sub y. And the same thing about the other equations. They're all the same. Now, I think the book probably wrote it like v initial x or something like that, which is stupid because it confuses us if you go further into physics. So we're going to stick with our nomenclature, which we started in class, which was VOX and VOY. That's the way most physicists write it. It's just a better way of doing things. Yeah. Those subscripts tell us something pretty cool, because if you look, there's a subscript or a letter name on every single variable except for one, which is time. Which means that all the motion in the x and the y direction is completely independent of each other, except for time. That is, the only thing linking my projectile motion, horizontally and vertically along some path is the time variable, which we'll prove to ourselves as things go along, and hopefully the exercises yesterday helped you see. So if we can solve for time, we can work on the x and y variables, and we can just basically see we're always going to set up two equations, one for x and one for y, that are related. And generally the y equation is going to revolve around free fall, and the x equation comes out pretty simply. I asked you about a guy on top of a cliff who drops a bullet straight down. It starts slow and it starts to speed up and faster and until hits the water and splashes. And it's a very heavy bullet apparently. And another one fires at the exact same moment, and it ends up firing some much longer, unless your gun is really lame, parabolic trajectory like this. A lot of people think that maybe a bullet, when it's fired for a gun, does something kind of like goes fast and starts to slow down from air resistance with time until it stops, and then it starts to fall. And that's how we thought physics worked for a very long time. That's not how it works in reality, though. In reality, it's following the whole time in a parabola, because that's what Newton proved, and we'll learn more about Isaac Newton later, and because gravity is always acting on the object as soon as it's in free fall, which we've proven before. And so with our cliff problem, you've got your cliff, the water. The two end up following the same time, because as the bullet's here, the fire bullet may already be way out here as this one starts to accelerate. This one drops at the same exact rate, and these aren't particularly pretty drawings. Let's try that again. Something more like this. Let's make the acceleration very obvious. There we go. Bigger. Something like here. Yeah, that's what we're looking for. And so I have this projectile motion straight down versus in a parabola. But if I look, each of these happens at the exact same time if I use like a strobograph, or I can use math to prove it. And what that means is my x and y motion is entirely independent. So even though my bullet was fired going really, really fast off the cliff, it doesn't matter, because all that fast was in the x, and gravity doesn't act in the x, at least at the surface of the Earth. And so it just acted like I dropped the bullet, which is pretty cool. These are like the simplest 2D kinematic equations, and the second problem, which is a bit more complicated. And these are the kinds of problems we're going to work with eventually, which is you have some, arbitrary launch angle theta at some launch velocity, and my projectile leaves. And what you're going to see, hopefully in time, is this might start off with some y velocity and a constant x velocity the whole way through. Like as the y slows down, the x doesn't. It gets to apogee, it's still going forward at the same x. It slows down, it's still going forward at the same x, but now gravity's starting to pull it down. And as it gets closer to the ground, that x is still the same, but gravity's pulling it harder. And if you balance these forces out, you end up seeing that you get a parabola, which is what we'd expect. And now we'll prove this by actually making these pictures ourselves with a football and our iPads. We'll use Motion Shot to do that when I get back. But these are how these problems normally end up working, And obviously, the only variable that we're actually going to end up solving for is, well, how long did it fly for? And that question is actually surprisingly easy to answer, although it can be a bit involved. And once you have that, you can figure out like how far it went, you can figure out what angle it was launched at if you were given the time, you can figure out the speed it was launched at, you can figure out its max height, you can figure out what angle you need to launch it to go certain distances, all kinds of interesting things, at least to me and a physicist. And hopefully you can see at least some utility in it. I think these are actually really fun problems. That's not just something I'm saying. And so when we're doing these problems, they end up working pretty well for us. And there are lots of problem-solving strategies. And I'm going to just link you to YouTube videos to watch after this, because honestly, they work pretty well. Now, they're going to do a few things differently. The first is, they might start off with a y equals y initial plus like, that's stupid. Apologies. Like initial velocity with respect to y, but they might use an I here. Remember, that's times time. This, we don't need this. If we're going to end up working with this, it will be obvious by the problem what to do with it, and I'll show you later. For now, let's just use the same kinematic equations we've been working with. Because, honestly, our initial y position can always be defined as 0, and y final can always be as where we go, and we can end up with the same problem. There are reasons for doing something like this, but honestly, for now, let's just ignore it. Let's start simple and build up to it, okay? So hopefully these videos help, and there's a brief mastering assignment. I don't expect you to necessarily even be able to do much of it, but those of you who click on and see math easily, this stuff does follow from what we've already learned, and for those of you for whom math is a bit more challenging, try to stick with this, try to take some notes from the video as if a professor were here giving lecture notes. Try to work along with him, and then if you try the mastering out tonight, work with someone when you get back to say, hey, I didn't get the right answer. Did you? And if they did, have them work. And if no one did, well, that's life, and we'll work from there. But hopefully we at least have an idea of whether this is good or bad once we get there. And the other thing to do is to consider there are only a few problem-solving strategies for these. And so in class over the next few days, we'll break down the different kinds of problems and do plenty of practice with them. So don't let this get too over your head. Right now, let's just let this be an introduction and work from there. And I hope I see you soon and that everything can kind of get back to more normal. But for now, thanks for putting up with everything and working with me. Have a good day.